So, physicist Gibbs introduced the concept of free energy. So sometimes it's called Gibbs free energy, and it's given the symbol G for Gibbs. And he made the definition. He said Gibbs free energy equals LH minus T delta S, or more likely, delta G equals delta H minus T delta S. So this was a definition that came from the previous argument, but now he's quantifying it a little bit more. And so delta G is a measure of free energy, which is also a measure of spontaneity. Is there enough energy for this reaction to happen spontaneously? So delta G equals delta H minus T delta S. So just from the argument that we saw a little while ago, if delta G is negative, then the reaction is spontaneous. Delta G is positive, then it's non-spontaneous. So we have the same free energy change delta G with the little circle again means standard free energy change. So that's at standard temperature, standard pressure, standard states. And so if we know the delta H and we know the delta S and we know the temperature, and the temperature needs to be in Kelvin, because remember that delta S values are joules per Kelvin, so we do have to convert temperature to Kelvin. So if we know those values, we can find out if a reaction is spontaneous or non-spontaneous. So what is the standard free energy change for the following reaction? Use the values of delta H and S from Appendix G. So we can first find the delta H for this reaction. I looked up the values for you. So the delta H of formation for elements, as we know, is 0, but if you look them up, it'll tell you it's 0, so that's good. So it's always good to look it up. In H3, the value for delta H is negative 45.9. Remember that you have to multiply by the coefficient. The S values are all non-zero, so we look up those values, and so I've gotten them there for you. And again, remember that it's always products minus reactants, and always make sure and multiply by the coefficient. So if you go through the math, delta H is, again, the products times their coefficients minus the reactants times their coefficients. In this case, the reactants are 0, so that one's easy. So 2 times negative 45.9 minus 0 is negative 91.8. Then we can find the delta S for this, and we can look up the numbers again in the Appendix G. Remember that none of these are 0, so we take the products. NH3 is 192.8, so 2 times 192.8, and the delta S for N2 gas is 191.6, and for H2 is 130.7. So if you subtract that, you get negative 198.1 joules per Kelvin. So remember that that's joules per Kelvin, which we'll see in a minute why that's important. And so we can finally get delta G by taking delta H minus T delta S. The one thing you want to be especially careful about is that remember that delta H is in kilojoules, so that's 91.8 kilojoules. Delta S is in joules per Kelvin, so it's it's negative 198.1 joules per Kelvin. So if you want to be able to add these together, they have to be in the same units. So that means I'm going to change delta S, divide by 1,000, and get negative 0.1981 kilojoules per Kelvin. So when the Kelvin cancels and we have kilojoules minus negative kilojoules, and we get negative 32.8 kilojoules is the delta G. So this is spontaneous. I was going to go back. We have a negative delta S, and just to point out that we're going from 4 gas molecules to 2 gas molecules, so it is getting more ordered. So it makes sense that delta S is negative. So now we can actually tabulate delta G just the same way that we did delta H and delta S. And so you actually have two options here when you want to calculate delta G, is that you can actually look up the delta G value. So again, just like the delta S and the delta H, you can find the delta G values for the products minus the reactants. If you happen to look up for that last example, what was it? Let me write it up here. We had H3H2 plus N2 plus 3H2 gives us 2NH2. Sorry, 2NH3 gas. If you look all these up, delta G for N2 is 0, for H2 is 0, and if you looked up NH3, it'd be 16.5 negative. So this would be negative 2 times 16.5 minus 0, so that would be negative 33.0 kilojoules. So notice that's slightly different from the last page, which was negative 32.8. So if you do it the two different ways, that's fine. They should be pretty close. They should be the same or at least really close. So don't worry if they're slightly different. You can choose either way that you want to do it. You'll see why the first way is better in a little while, because if temperature changes, then we have to use the first equation, but you can do this one either way. I think I have another example on the next slide. Yeah, so here let's calculate delta G for the combustion of 1 mole of ethanol at 25 degrees C. So remember that all the values on Appendix G are all at 25 degrees C. So that's where we're looking up these values. So we're going to use the standard values given in Appendix G. So this time we're actually looking up the delta G of formation values for these. The delta G for elements are also 0. So the delta H and the delta G are 0, but the S values are not 0. Anyway, again, look up the values from the table. Delta G, H of ethanol is 174.8, negative 174.8. Okay, so once you plug those numbers in, 2 times negative 394.4 plus 3 times negative 228.6, and then minus a negative 174.8, and that gives you negative 1299.8. So this is a spontaneous reaction, which you should already kind of realize that. If you take alcohol and you burn it with oxygen, you are going to get flames and you're going to get CO2 and H2O produced. So that is a spontaneous reaction. So I know we make hard and fast rules. So, delta G equal to 0 tends to be what we call equilibrium, but we're going to kind of make a little bit of a wider range. So if delta G is a negative number smaller than negative 10, so more negative than negative 10 kilojoules, then we consider that reaction spontaneous as written. Just about probably 99.9% of all the reactants will convert into products. Once equilibrium is reached, products predominate. If delta G is a large positive number greater than 10 kilojoules, then the reaction is non-spontaneous as written. The reaction will not go. There will be very insignificant amounts of product. However, the reverse reaction would be spontaneous. And of course, we've got our in-between. So if delta G is between negative 10 and positive 10, so it's close to 0, the reaction really is an equilibrium mixture with significant amounts of both reactants and products present. So where's this all come? Why is it called Gibbs free energy? Well, it all has to do with the fact that any kind of reaction theoretically can give work, or we can obtain work from any particular reaction. if we burn gasoline out in a field, we're not going to get much work from it. However, if we combust gasoline in our tank, in our car, in pistons, the combustion of the gasoline will move the pistons will move other things, and so then our car will work. So you can generate electricity, or you can get some kind of work out of the combustion of gasoline. So reactions can be used to obtain useful work. And so, like I said, often reactions are not carried out that way. Like I said, if you just burn a gallon of gasoline out in a field, nothing's going to happen. You're not going to get work for it. Or we talked earlier about other kind of reactions. If you just put zinc in hydrochloric acid, but you leave it open to the room, the reaction will happen, but you're not going to get any work from it because you don't have it geared up to do that. No useful work is obtained, but it's still possible to get work. And so, in principle, if we carry out this reaction, we get the maximum amount of work that we can get means that no entropy is produced. In other words, we have totally gotten all the work out of it that we can. So for a spontaneous reaction, the amount of work, the most work that we can get out is equal to delta G. And so that's where the name Gibbs free energy came from, because it's the amount of free energy the amount of energy that is free to be used for work. So the maximum energy available or free to do useful work. And that's the energy that can be used. Again, we always fall short of that. We're not able to use it all. There may be the setup maybe didn't use up everything, or it's impossible. Just like in the lab, you can't scrape up every bit. However, so it's not possible to reach maximum work, and that's why entropy is created. But that's where the name Gibbs free energy comes from, is it's the amount of energy that is free to do useful work. Okay, so as a system approaches equilibrium, the Gibbs free energy approaches zero. And we can look at the next picture and see what happens during a spontaneous reaction. As the reaction proceeds, the free energy is used and eventually reaches zero, or a minimum value. And that's where delta G equals 0, and so the reaction stops. It doesn't really stop. The net reaction stops, and it comes to equilibrium. It looks sort of like this. At the spontaneous reaction, so the Gibbs free energy decreases, and then eventually we come to equilibrium. Okay, so in the figure on the next slide, you can see that the free energy during a non-spontaneous reaction would have to go uphill. And so that's why it's positive. So in this case, we start at equilibrium down here, and then the Gibbs free energy has to increase for a non-spontaneous reaction. Okay, so here's an equation. We're not going to talk about where it comes from or how it's derived, but let's talk about it. This is, so again, delta G is Gibbs free energy. This is the energy change, the free energy change when reactants are in non-standard state. So that's why we don't, the little circle again means standard conditions. This delta G without the circle means at other non-standard states. So it's equal to the delta G at standard conditions, and then it's got this little correction here that we can use. So this R is the R that we've been using, 8.31 joules per mole Kelvin. And temperature has to be in Kelvin. And then you may or may not remember what this is, but Q is that equilibrium quotient. So if you remember when we write, let's say we have a equation C plus D. If we're at equilibrium, we can write the equilibrium expression where it's the concentration of C raised to the C power, the concentration of D raised to the D power, etc. If we're at equilibrium, this is true. K will equal this ratio whenever it will always come to that kind of a ratio when it reaches equilibrium. However, remember the Q is when they're at non-equilibrium. So like if we change this to Q, and this would be like initial. So not necessarily at equilibrium, but whatever the ratio are, that is the Q. So whatever the concentrations are, you can find Q, plug it into here, and this equation is true. So what does that mean? So we can find delta G at other non-standard conditions. So that's useful, but what we're going to do is we're going to use this information to find the relationship between delta G and K, the equilibrium constant. So again, delta G is the change in free energy at some point in a reaction as it approaches equilibrium. Since we have Q, which is that quotient, we're not at equilibrium yet, and so this equation holds. But once we get to equilibrium, then Q becomes K, and delta G becomes 0. So the delta G of that reaction becomes 0, and Q becomes K. So we can rewrite that equation, and this is the important thing that I want you to get out of it, is how is delta G related to K? So the delta G of the generic reaction, not necessarily at standard conditions, will equal delta G for the standard conditions plus RT, natural log of the equilibrium constant, K. So we're at equilibrium now. So if we rearrange this equation, here's what we get. So this is the important equation to remember. Delta G, the Gibbs free energy, is equal to negative RT natural log of K. So if you know the delta G, you can find the K value. If you know the K value, you can find the delta G. Remember again that R equals 8.31. It's just a constant, joules per mole Kelvin. T has to be in Kelvin so that it cancels out. There we go. There's R down here, and you can solve for one or the other. You want to be careful, as we'll see in the next example. One important thing is that R is in terms of joules, just like we saw earlier. Delta G is generally in terms of kilojoules, and so we want to make sure that we have the units correct if we're doing problems with this. But what I wanted to point out here is how they're related. So let's say that delta G is a negative number. What does that mean? That means the reaction is spontaneous. So if we have a reaction, let's just write it, A plus B, C plus D. So if we have a reaction that's spontaneous, that means products predominate, right? And since, remember, we had I can write this over here, we had our K expression. I'm not going to put the coefficients there, the superscripts, but you know what I'm talking about. They're not necessary for this. So if products predominate, that means K is greater than 1. So if K is greater than 1, products predominate, it's a spontaneous reaction, and delta G should be negative. So let's look at this equation. If K is a number greater than 1, the natural log of K is a positive number. A positive number times a negative here will give me a negative number, and so delta G will be negative. If K is less than 1, what does that mean? That means the reactants predominate, A and B. So this is K less than 1, reactants predominate. Products predominate if K is greater than 1. So if K is less than 1, so K less than 1, then the natural log of K is a negative number. And a negative times negative will give me a positive delta G. That means it's not spontaneous. So if K is very small, that means reactants predominate. It's not a spontaneous reaction. So this equation is really important, just that you see that relationship. If K is greater than 1, products predominate, and delta G is negative, meaning it's spontaneous. If K is less than 1, that means it's reactants predominate, and delta G will be positive, meaning it's a non-spontaneous reaction. So K and delta G are definitely related to each other, and so this reaction is an important one. So let's see, maybe I can erase some of this so that you can see the words there. Okay, so again, when K is greater than 1, natural log of K is positive, delta G is negative. If K is less than 1, the natural log of K is a negative number, so delta G will be a positive number. So just what I got through saying. Now we can use one to solve for the other. So here's the problem. Find the value of the equilibrium constant K for the following reaction. In this case, they're telling you what delta G is. Delta G is negative 13.6 kilojoules. If you weren't given this value, probably somewhere along the line, they would tell you to find it. So I believe we found it on a previous slide, a few slides ago, but you can look up these values in Appendix G and take our products minus our reactants. I believe I remember this because this one wasn't in the table, but they gave it to you. So you would be either given the number or told to look them up in the Appendix G. If you don't know any better, that's where I would look, Appendix G. So anyway, if you take the delta G products minus reactants, made sure to multiply by the coefficient, you would get negative 13.6 kilojoules. So now we can plug them into our equation. Delta G equals negative RT natural log of K. If we divide both sides by negative RT, we get this equation. And now if we plug our numbers in, this is negative 13.6. You want to be careful because this is kilojoules. And then R is 8.31 joules per Kelvin, per mole Kelvin. And so if you're going to keep this in kilojoules, you want to make this kilojoules, 0.00831 kilojoules, and then 298, that's Kelvin, 298 Kelvin. So that'll cancel. So now the kilojoules will cancel, and we'll just have a number actually, because K doesn't have units. So that would equal 5.49 if you do that number, because the 2, this is negative here, negative RT, delta G is negative, so this is a positive number or a number greater than 1. So then we have natural log of K equals 5.49. To undo the natural log, you have to raise it to both sides to E. If you raise E to the natural log, they cancel. So you just get K. And then this side E to the 5.49. And so if you take E to the 5.49, you'll get the answer. It's probably on the next slide. Yeah, now notice here, this time, in this case, I converted kilojoules, delta G into joules. So either way, it doesn't matter because joules per mole, the moles will cancel, the joules will cancel. So either convert 8.31 to kilojoules or convert your delta G to joules. just don't forget that. So 5.49, and then if we take both sides, take e raised to both sides, then we get k equals 2.42 times 10 to the second, or we see that's 242. So let's just think about that. The k is larger than 1, and that means products predominate. That makes sense because delta G is negative, and so it's a spontaneous reaction. Now, in just thinking through what we talked about earlier, notice that negative 13.6 is not very large. It's just remember we said from negative 10 to positive 10 was kind of equilibrium. So this isn't too far off of it. So because this is a negative 13.6, then 242 is not very large either. So the products predominate. It may not be 99% or whatever, but it's definitely products predominate. If this was a much bigger negative number, negative 252, then this would be a much larger k value. Might be to the 10 to the 8th or something like that, very big. So they are related that way. And just notice that because G is negative, we do expect K to be greater than 1. So it's spontaneous and products predominate. All right, so now we're going to look at the relationship between something being spontaneous and how the temperature might change that, and how the enthalpy, the heat of reaction, and the randomness of the reaction have an effect on spontaneity. So we're gonna take it all in. Before, well, I'll give you an example once we get to it. But I just wanted to review really quickly. So what is? Make sure that's it. Okay, remember that delta H. If it's positive, it's endothermic, and if it's negative, it's exothermic. Delta S, if it's positive, it's becoming more random, increased entropy, and if it's negative, it's less random. And then remember that delta G, of course, negative is spontaneous and positive is non-spontaneous. So let's, before I put the next slide on, let's talk about the example. Let's say I have an exothermic reaction. So delta H is negative, and I have it's becoming more random. So both of those things tend to be spontaneous. We know that those things tend to be spontaneous. So if something's exothermic, this term right here, the delta H term is negative. And then if delta S is positive, then this term is negative. And so delta G will always be negative, which means the reaction will always be spontaneous. So now let me show you the chart here. All right, so if delta H is negative, delta S is positive, so it's becoming more random, it's exothermic, all of those things make something spontaneous. Delta G, no matter what the temperature is, it doesn't matter, no matter what the temperature is, this delta G will be negative no matter what under these conditions, and so that reaction will always be spontaneous. Let me think of an example of that. So let's say we took our, we saw that earlier. We took our alcohol, and we burned it. So alcohol was exothermic. Obviously, it's going to give off heat, so that's exothermic. And we saw that it was like a C2H5OH. It was a big, large liquid molecule, and it becomes, it's going to add with oxygen, and it's going to give me CO2 plus H2O. It's going to be 2, and I think it's 2 here. Anyway, the numbers don't matter, but we're going from a liquid to all gas. So this is becoming more random. So this is an example of this reaction. No matter what, if you put a flame to alcohol, it's going to burn. There's nothing stopping. It doesn't matter how cold it is, how hot it is, it's going to burn. So that is spontaneous at all temperatures. The opposite of that would be if it's an endothermic reaction. So if delta H is positive, and if it's becoming more ordered, delta S is negative, so that means delta G will be positive no matter what, and those reactions will never be spontaneous. I don't know if I can think of one off the top of my head. Something that's becoming more ordered and endothermic is just not ever going to be spontaneous. But now, some of these that are in the middle. So let's think of an example I had talked about earlier. I'm going to erase this here. Remember I talked about an ice cube. So let's say we take an ice cube and we put it in room temperature, in a room that's at normal room temperature. What's going to happen? Well, we know that the ice cube's going to melt. And is that endothermic or endothermic? Endothermic or exothermic? Endothermic, yeah. Delta H is positive because to melt ice, we have to put energy in. If ice melts, is that more random or less random? Well, it's going from solid to liquid, so delta S is more random. So let's think about that. Here, delta H is positive, it's endothermic, and delta S is positive. So that doesn't fit any of the two we've gone over, but it's this bottom one here. Delta H is positive and delta S is positive. Well, will delta G be negative or positive? Well, it depends on the balance between delta H and delta S, and mostly, I'm going to erase this here, mostly it's going to depend on the temperature, right? Because let's see, if delta S is positive and delta H is positive. At relatively low temperatures, the negative number will be smaller than the positive number, so overall the reaction will be positive or non-spontaneous. But at higher temperatures, this term then becomes more dominant, the negative term becomes more dominant, and it'll become spontaneous. I'm sorry, I'm down here. It'll become spontaneous at higher temperatures. And that's exactly what happens with our ice cubes. If we keep the ice cube in the freezer, in other words, at relatively low temperatures, the positive delta H takes over and that ice won't melt. It'll be non-spontaneous. But at room temperature, which is a relatively higher temperature, the negative term takes over, the randomness takes over, and so that ice cube will melt. And so it will depend on what the T is. Now the same is true, so that was this bottom one, that example. The same is true of if they're both negative. So if it's an exothermic reaction, but it's becoming more ordered, something's becoming more ordered, which would be the reverse of this. So let's say we're taking water and we're wanting to freeze it. Okay, if we're taking water and we're trying to freeze it, that's going to be exothermic. It gives off heat. It's also becoming more ordered, and so that's where they're both negative. That's going to happen at low temperatures, but not at high temperatures, so that's just the opposite. So you can figure out, depending on if delta S is negative or positive, you can sort of see that sometimes reactions are always spontaneous, sometimes they're never spontaneous, and sometimes it will depend on the temperature. So we can actually go a step further and figure out what that temperature is. If we're trying to, so if we're using our delta G equals delta H minus T delta S, first of all, what we're going to do is we assume that delta H and delta S are constant with respect to temperature. So if we look up on the chart delta H and delta S, even though they're technically at 25 degrees, we can use them in any of these equations. However, delta G definitely depends on temperature, and so we have to calculate what the delta G is at different temperatures. So we can find the delta H and delta S at 25 degrees, substitute them in this equation, And if we know the temperature, we can find out if delta G is positive or negative. Or as you'll see in a minute, if you know the delta G, you can find out what temperature that's going to become positive or negative. So anyway, let's look at that. So again, if the temperature is something other than 25, you have to use this equation and make sure, again, that temperature is in Kelvin. So let's look at this example. Calcium carbonate, which is, basically chalk and limestone, all of those things are made out of calcium carbonate. And if you take calcium carbonate over time, it can decompose into calcium oxide, which is quicklime, and carbon dioxide is is released. That's often what happens on chalky ground, is they carbon dioxide is released and we can get these holes in the ground. Anyway, the question is this reaction spontaneous at these two different temperatures, at 25 degrees Celsius or at 1200 degrees Celsius? And then let's see if they're spontaneous or not. So like I said, you can use the equation. You're going to find delta H and delta S at 25 degrees and then plug them into the equation. So the delta H formation is, you can see for calcium carbonate is negative 1220, for calcium oxide negative 634.9, for carbon dioxide gas negative 393.5. So you take the products times their coefficient minus the reactants times their coefficients, and then you can see the S values that I looked up in the appendix G. And again, I find delta G, and I'm sorry, delta S. So calculate using the summation line. So we're going to just plug this into the equation. We're going to go and look up the delta H and the delta S values, or the S values from the back of the from the appendix. So there's the delta H of formation at 25 degrees, the S values at 25 degrees. We can find delta H by taking the products times their coefficients minus the reactants. So if we plug those numbers in, we get 191.6. So this is an endothermic reaction. Delta H is positive. Now we've got, again, if we use the S values, we take the products minus the reactants, and we get 141.9 joules per Kelvin. So this is it's becoming more random, is more disorder. We're going from a solid to a solid and gas, so that is more random. So delta S is positive. And now we can plug it into our equation, so we can substitute H, S, and T into the equation. Remember, you can see here that I converted delta S to kilojoules before plugging it in the equation, because we need the kilojoules to cancel, or to add together actually. So make sure and divide by 1,000 before you plug it into the equation. So delta G equals delta H minus T delta S. Don't again forget to convert T to Kelvin. So we have our delta H minus 298 times 0.1419 kilojoules. So the kilojoules will cancel. I'm sorry, the Kelvin will cancel and the kilojoules will combine. And so we have delta G at 25 degrees is 149.3. Of course, we could also look up the delta G values from the appendix, and we should get a very close value if we looked up the delta G for these three values. So this is a non-spontaneous reaction at 25 degrees because delta G is positive. Now let's plug them in at 1200 degrees. So 1200 degrees Celsius is 1473 Kelvin, and use the same H and S as before, again making sure to convert delta S to kilojoules. So if we plug those numbers in, we get delta G is negative 17 kilojoules, which is spontaneous. So this reaction is spontaneous at 1200 degrees. So this is one of those examples we saw that if both delta H and delta S are positive, then it will be spontaneous at relatively high temperatures and non-spontaneous at low temperatures. So how do you know what that means? What is relatively high? Well, let's see, at what temperature will this change over from spontaneous to non-spontaneous? Well, where's the spot where delta G goes from positive to negative? That would be 0. What you can do is you can rearrange the equation. Let's see there, that's missing. So we can set delta G at 0. So remember, delta G equals delta H minus T delta S. And if delta G is 0, so if we put 0 in for that, then we bring delta, so then we have delta H equals T delta S. And then if we divide both sides by delta S, then we get T equals delta H over delta S. Again, don't forget this has to be in kilojoules so that they can cancel. So if you plug the delta H in, divide by the delta S in terms of kilojoules, we get the temperature in Kelvin where the reaction goes from non-spontaneous, which is less than 0, to spontaneous, which is greater than 0. So at 1077 degrees Celsius, this reaction changed from non-spontaneous to spontaneous. So just something to consider. So that's the end of this chapter. You should be able to predict the sign of entropy change of a reaction, meaning delta S. So you should be able to look at a reaction and be able to predict, is it going to be positive or negative, the entropy. You should be able to calculate delta S for any reaction or phase change. You should be able to calculate delta G if you know delta H and delta S. Or you should also be able to calculate delta G from the standard free energies of formation from Appendix G. So all of these values from Appendix G. Be able to interpret the sign of delta G, meaning knowing if it's spontaneous or not spontaneous, and also how does it relate to the signs of delta H and delta S. So that sort of that table that I introduced a while ago. Be able to write expressions for a thermodynamic equilibrium constant, and be able to calculate the K if you know G, and be able to calculate G if you know K. So that's and then be able to calculate delta G at various temperatures from delta S and delta H, and also be able to calculate K at, if you know G, whatever temperature it is, be able to calculate K as well. So I believe that's the end of that.